Good afternoon, everyone. I'm Shannon Durejo from Creamer Media. Welcome to today's webinar, which is brought to you by Industrial Water Cooling. The discussion today will focus on the use of air-cooled condensers for recoverable energy and power generation, where a panel of professors will explore the cutting-edge concept of induced draft air-cooled condensers incorporating partial evaporative cooling and their transformative role in harnessing recoverable energy for power generation. Before we begin, please take note of the following. To encourage interaction, we have enabled the chat and the Q&A. Please post your questions into the Q&A, which you'll find at the bottom of your screen. The panelists will answer as many of your questions as possible during the session. You can also interact with the panelists and the other attendees in the chat, which you'll also find at the bottom of your screen. Please remember not to post any questions into the chat though, as we might miss them. Use the Q&A for questions. Please be aware that we are recording this webinar. We'll send you a copy of the recording when it's available. We're also streaming the webinar live to YouTube and we'll share the link in the chat. To get started, I'd like to introduce you to today's facilitator, Hanno Reuter. Hanno recently joined the IWC in a consulting and R&D capacity. He is a mechanical engineer with several degrees from Stellenbosch University. With 26 years of industry experience and 12 years as a registered professional engineer, he specializes in thermofluids, performance modeling, and thermal power plants. He's also an extraordinary professor at Stellenbosch University. Hanno will be discussing air-cooled condensers with a panel consisting of Professor Mike Owen, head of the Thermodynamics and Fluid Mechanics Division at Stellenbosch University's Department of Mechanical and Mechatronic Engineering, Professor Johan van der Spey, Fluid Mechanics and Turbo Machinery Lecturer at Stellenbosch University, and Professor Chris Meyer, also from Stellenbosch University. I'll hand over now to Dr. Hanno Reuter to start the discussion. Over to you, Hanno.
Thank you, Shannon. You can see my screen? Right. Can you see my screen? Everything clear?
Looking good, yes.
All right, excellent. Thank you, Shannon, for this opportunity, and thanks for my colleagues for joining me on the panel. I must just add something there, Shannon. Professor van der Spey is head of the department at Mechanical Mechatronic Engineering. I think he's a modest guy. He didn't include that in his bio. Yes, so I'll be discussing recoverable energy power generation using air-cooled condensers. This word, recoverable energy, I haven't really come across so much in my time as engineer, and it originated from a discussion with Professor Wickert van die Kerk, who's now currently the Dean at Mechanical Engineering. And I was talking to him about what we're busy with, and it's heat rate improvement, efficiency improvement of systems, and that it's better than renewable energy. And he said, yeah, but it's actually recoverable energy. So it's a word that I've adopted, and I think it's a word that might change people's mindset on this topic. So yes, thanks for this opportunity. I'll be discussing the following. I'll give you a slight introduction just to give some context, then just to inform people of the significant role that South Africa has played in the development of air-cooled condenser technology. And then just describe some of the technologies of old and new developments that we're busy with. I'll tell you how one can improve power plant performance by enhancing air-cooled condensers, and then give you some numbers from case studies that were done, conclusions. And then obviously afterwards we'll pose some questions to the panelists to initiate some discussion on this topic, and to hopefully make it clearer how interesting and important this topic is. So to commence with the introduction, I think the word recoverable energy power generation, or the term, it means increasing annual power output of power plants by technology enhancement and improved operation and maintenance. And I think the people out there aren't aware of the amount of energy that can be converted into power out there that's not harnessed at this stage. I make a claim it's the most economical and clean power available. And that's something we'll discuss later. Then going to the next bullet, new air-cooled condenser technology to enhance power output of thermal power plants. So the air-cooled condenser is an old technology, but by improving it, significant improvement in output can be achieved. So what is an air-cooled condenser? I forgot to add this here, but it's coming later. It's effectively a system by which we condense the steam from the steam turbine exhaust directly with air-cooled flint tube heat exchangers. I'll go into a little bit more detail later, but this system was developed pretty much. A lot of the developments were done at Stellenbosch University, and the models used for thermal design and CFD models used worldwide were developed at Stellenbosch University under the leadership of Professor Detlef Kruger, who's unfortunately passed away. And the state-of-the-art Medupi and Kusile air-cooled condensers were basically designed by Stellenbosch University, by the team of Professor Detlef Kruger. By this, I mean designed, the specifications were prepared by Stellenbosch University. Then interesting for us is that forced draft and induced draft conventional and new air-cooled condensers and new hybrid technology were developed in South Africa, proudly in South Africa by IWC's research and development team, in close collaboration with Stellenbosch University, with a gentleman sitting in the panel. And we've had some support from Electric Power Research Institute in the US and Horizon 2020. Then interesting, these systems are quite wind sensitive, so wind mitigating devices and design rules were also developed at Stellenbosch. And new fans have been developed, probably the most efficient fans out there by Notice. Professor Chris Meyer is on the panel today. He's managing director at Notice. And we've done various testing at Stellenbosch University. So also, we're very involved internationally to verify flint tube performance testing. Maybe just to say, give some numbers just to get you interested. Eskom Matimba power station when it was built was the largest in the world. And one has found that during periods of high ambient temperature and wind speeds, there are sometimes up to 25% load losses, which could be recovered by retrofitting the air-cooled condenser with improved technologies. I'll show you the numbers later on. 25% of 4 gigawatts is 1 gigawatt, which is a lot. Then Eskom Majuba is a very interesting power plant. Also, to illustrate a few points, this is a power plant that is half of the power plant is dry cooled and the other half is wet cooled. And then one can see that there's a significant, about a 70 megawatt difference per unit, just due to the type of cooling system. So essentially, the air-cooled condenser unit produces 9.3% less net power output at design conditions than the wet-cooled system. And what is unique is that the power plants for wet-cooled and dry-cooled are identical, except for the cold end. So that illustrates the significant difference in power output just due to the type of cooling one uses. But a timeline just to show how much was done in South Africa over the years. So if one looks at 1972, the first plant was built in Namibia, which was for a 120 megawatt steam turbine. And at its time, it was the first large ACC in Africa. Then I put this wire deck in because this was the first considered to be large air-cooled condenser plant in the world. And that was in 1978. And that remained the largest until the largest, the world record plant was built in Lephalale, Ellisras at the time, known as Matimba. So you see there's a jump from 400 megawatts to 6 times 650 megawatts, 665 megawatts, excuse me. And this plant was considered to be an engineering feat. It was a wonder of the world almost, because it's really something special. I'll show you some pictures just now. Then Majuba followed closely after. And then I put this one in because this is where I got involved in air-cooled condensers. So I was working for GA Air-Cooled Systems for a 50 megawatt plant. Then in 2016, another groundbreaking air-cooled condenser. The Key Solar 1 concentrated solar plant in Uppington is a 50 megawatt plant with two hours of storage. It was the first natural draft air-cooled condenser from what I'm aware of. And it's the tallest natural draft cooling tower in the world at the time. Recently, built a larger one, but this it was over 200 meters high. Then Medupi, which everyone knows, is 6 times 800 megawatt. There are very different classifications of what is the largest, but it's definitely one of the largest in the world just due to the fact that it's a 6 times 800 unit altogether in one. Kusile, very much the same. These are both still under construction in a way. Many of the units are operational, but it's ongoing. And then an interesting plant which I visited 2 weeks ago is the Redstone CSP. It's under construction. It's in Postmasburg, close to Postmasburg. It's a central receiver plant, and it has 12 hours of thermal storage at full load. And this plant, what makes it interesting, it's the first induced draft air-cooled condenser in South Africa. So this is a different type of technology that's also now available in South Africa. So the role that I just maybe want to stress is most groundbreaking ACC technologies were first built in South Africa. And I think people are not aware of this. And air-cooled condensers are very popular in the world. They're built worldwide at the moment. So it's something we can be proud of. And then I think there were people that were very instrumental in the development and the fact that these plants were built, and that was Professor Dr. Reuter. His researchers and students from Stellenbosch University had a profound contribution to ultimately published in a book, which is really used worldwide as a reference. And then there was Mr. Franz Vogt. I don't have his name here, but he was the pioneer in air-cooled condensers. He was the brainchild, or the Matimba was his brainchild. What are air-cooled condensers now? Let's just give you a bit of more detail here. So as I said before, it's a system that's used in steam power plants to condense turbine exhaust steam directly in air-cooled fin tube heat exchangers. The main components are the fin tubes, and the current fin tubes that are used. Some companies have now recently developed some slight changes, but the flat tube technology was actually developed by Professor Detlef Kruger in collaboration with Loomis at the time. I'll tell you a picture just now to show you what it looked like. Then maybe just what I told you earlier, compared to plants that have wet cooling towers or wet cooled plants, with the same boiler design, i.e. same fuel consumption and greenhouse gas emissions, the ACC has advantages, but it also has disadvantages to wet cooling. So essentially the main advantage, and that is why we use it in South Africa, because we have a scarcity of water. So the main advantage is it consumes no water as a cooling system, as opposed to 1.5 to 2.5 liters per kilowatt hour for cooling towers. So that means if you have your heater on for 2 hours, you consume somewhere at a plant, you're consuming about 5 liters of water if the power comes from a wet cooled plant. The drawback, of course, is that the plant efficiency and output is significantly less. So it produces up to 10%. It depends on the design, of course, but I've encountered that it produces up to 10% less power output at design conditions than a wet cooled plant. And at high ambient temperatures, this goes up to 20%, which is significant. That means for the same fuel combustion, the same emissions, you're getting between 10 and 20% less power output out of a plant which is dry cooled. And then we've also experienced that it can produce up to 35% less power output at high ambient temperatures of say 40 degrees plus, and if there are high wind speeds as well. What happens is the plants, the back pressures reach alarm levels, the plants have to be deloaded, or sometimes they even trip. And this is actually quite catastrophic, even though it seems to be quite common and frequent at the moment. So the air-cooled condenser, as I say, the main components, I think I should have added as well, the fin tubes as well as the fans. The fans are a crucial component. But here you see, just to show you what the fin tube technology looks like, it was developed here and that's used worldwide. It's a flat tube design. So the steam, it's a carbon steel tube and the steam is inside the tubes. And then you have these fins, aluminium fins that are brazed onto it. And air passes through these fins and it cools the tube and it allows the steam to condense inside the tube. So that's the technology. So, and to show you a few pictures of what these plants look like. So this is Eskom Matimba's ACC, air-cooled condenser. So the air-cooled condenser is in the front here. This photo was taken from the archives of Professor Kroger, and this one was taken from the internet. So these units, here we have 48 fan units. So it's 48 fans per boiler. That are required to drive the air through the heat exchangers. This height of this platform is 50 meters above the ground. These fans have a diameter of 9 meters per second, 9 meters. If you think of an airplane, a Cessna 172, it has a wingspan of 11 meters. So in such a fan, we have 8 blades, 8 wings of such a plane almost, rotating, and they are driven by 270 kilowatt motors. That means per whole plant, we have about 70 megawatts of power required just to drive the fans of this air-cooled condenser, which is effectively almost a full new renewable energy power plant that's currently built like Redstone, for instance. What else did I want to say? Now there are a couple of other photos coming. Then this is it was a really beautiful site. I was at this plant 2 weeks ago. This is an air-cooled condenser, which is unique. It's a natural draft air-cooled condenser. Usually, as I've said, one uses fans to cool the fin tubes. But here one uses a natural draft tower, which is effectively the power tower, which houses the central receiver. So this tower is hollow, and the airflow is affected by buoyancy effects due to density differences between inside and outside this tower. And it's really simple, and it seems to work seamlessly, very, very well. This is also a unique design, as I said earlier, for South Africa. Then Medupi. Everyone knows about Medupi, but what they don't know is that this air-cooled condenser is probably the best one in the world. From all the information I've got, it's operating better than expected, and there were 10 design changes done to this condenser before it was built to upgrade it from previous design rules. It's effectively twice the size of Medupi, Matimba, if I'm not mistaken. So here we have 34-foot fans, and these are 64 fan units per boiler. This was when it was under construction. So when I go to India, the first thing they ask me, do I have a video? It seems like people need to see a video. So I've got short videos for you, 2-minute videos. I'll quickly play them. Just one moment, I need to stop sharing and reshare. You see my screen?
Yes, we can.
All right. I'll take you through this. There's no music or anything. It's my voice that will tell you what you're seeing. So just to start off, this is a unit that we just designed. It's typically for a 20 megawatt steam turbine for small biomass type plant. And here you already see this is a steam duct and the air-cooled condenser. So as we move through, I'll explain what you see. So the steam duct It takes the steam from a steam turbine all the way to the fin tube bundles. And these bundles are housed here. These are the bundles I showed you earlier. Then one has a wind wall around to shield the bundles from the wind. Here we're inside, you see the fan bridge, which has the fan assembly. There's a motor, a gearbox, and a fan. The fan runs inside a fan ring or a fan casing. And in between each unit, you have these plenum partition walls. Then you go outside, you see some special features, IWC features, which were developed at Stellenbosch University, this platform here and wind cross at the bottom. So how it works, the fans draw air from the environment and blows this air through these fin tube bundles. So you see the streamlines, typical streamline of the air. Inside the system, you have steam coming from a steam turbine, and it goes inside the main steam duct, and then is distributed inside these heat exchangers, where it condenses inside the bundles and leaves the bottom as liquid water, and that allows the pumps to repressurize it for the boiler. So this liquid water then drains into this condensate tank at the bottom here. And this is a forced draft arrangement. So the air is blown in from the bottom. The fan is below the heat exchangers. So it blows the air through the bundles. And this is the technology that's been used up to recent times, I think up to about 10 years ago. And it's often preferred due to the track record and the fact that many references exist on this technology. All right. Then the next one is a new technology that was developed by IWC. So this is an induced draft arrangement. So you see, it looks quite different from the forced draft arrangement. And I'll point out a few details which are unique. So the steam duct is at the bottom. Then you have the fans on the top. And these fans, having them at the top makes the system less wind sensitive has less flow losses, which allows the unit to be smaller. So here you see in the floor, you see these gratings, so to speak. This is where we put in a booster system called the hybrid deflecmator, and you'll see it underneath. I'll tell you the details just now. This is incorporated into the air-cooled condenser, and it has the impact of a supercharger for the air-cooled condenser. So it's an evaporative system to enhance the performance dramatically. Then also the system of ours has a fan stack with a diffuser, which allows for improved fan efficiency, all enhancing performance. So here you see the streamlines as they flow through the air flows through the system. And here you see the steam again passing inside the duct, and then condensing inside counterflow. Inside counterflow heat exchangers. So slightly different from previous technologies. It's buffering now, apologies. Right, so it's got a few differences. Then also you can see we have a ventilated access ladder, which is different from competitors. It also allows for ventilation of the mechanicals. Sorry for that. So you see the condensate here running down as with the previous one and back into the condensate tank. So it's quite different in the sense that the steam enters the bundles from the bottom as opposed to the top. That allows for a number of advantages. My whole system is supported at ground level. Each part of it has its own foundation, which I believe is a significant advantage. We also have significant improvements on erection. Ultimately, the system is 5% more compact and has expected 20% less steel requirements than a forced draft unit. So there's a significant cost impact as well, saving. I'm sorry for this buffering. I'm not sure what's causing it. The videos aren't always that good. All right, I think I've got another slide which illustrates everything again. So I'll stop that and return to my, stop sharing that. All right. Just want to check something, sorry. I think I missed this slide and I was wondering why I did that. But in any case, so in principle, I just wanted to show you this. This is a very simple diagram. So you've got the steam turbine, steam exits the exhaust and flows inside this duct, which you saw, condenses inside of fin tube bundles, condensate is returned to the boiler. Then you have the fan, which is a crucial component, which blows the air across the air-cooled condenser fin tube bundles. Right, just to show that again in relation to that. All right, so the IWC force draft, now that you less of a seasick experience. So we'll just quickly to recap, you see the steam duct, see the bundles, the fan assemblies, and you got the wind walls. You have the wind cross, which is very crucial for wind effects. Then for the induced draft, I was fortunate enough to visit the Toantic plant near New York in the US. This was built by Enexio, and the same company that built the Medupi air-cooled condenser. And this is the first the company that first built induced draft air-cooled condensers, just to show you how much different it looks from the forced draft unit, and give you a sense of scale. You see these are the steam ducts that supply the steam. In this case, the steam enters the top. In our case, the steam will enter the bottom. And here you see what I said. Typically, this is what a fan assembly would look like, with the fan blades, which resemble an aircraft wing. All right, the new air-cooled condenser of IWC. What I want to point out, this is it has a few design features that are unique. And one of them is the ventilated walkways and the ladders, and also a structure by which one can lower the fan, drive, and maintain it at ground level quite easily. So what we've done as well is we've split the steam header here at the bottom in order to be able to fit a hybrid deflecmator or evaporative cooling booster unit between the ducts. There's some numbers just now that I'll give just now. So this is in between this the steam duct. What it looks like is as I show here, it's effectively a heat exchanger with bare tube bundle, bare tube heat exchanger. You see over here, and then it has a water distribution system, so one can spray water onto this bundle. And this water then falls into a basin and is just recirculated. So steam enters the hybrid deflecmator through a steam duct here, and then it condenses inside these tubes. This system can be operated dry without any evaporative cooling, as well as wet when one needs the boosting. Another way of doing it is one that was developed in a Horizon 2020 project, which looked something like this, where the hybrid deflecmator is incorporated into a air-cooled condenser bank, and it's effectively connected to the same steam duct, and that has the same boosting effect. I'll give you the numbers just now. Then this is the IWC version of it. So as you can see, this is a 3D render of a forced draft hybrid deflecmator. So the bundles you'll see here, the steam duct, the bundles, and then one has a water collecting system, which are a water collecting device which catches the water that's recirculated, guides it into a water basin in order to have it recirculated. And this water collection system allows air to pass through and water to be collected. So in the forced draft case, the fan pushes the air across this bundle. So in this case, one has a fan. In the previous one, you see the bundle was incorporated, so it was making use of the fan of the induced draft ATC to be ventilated. This one needs a dedicated fan to function properly. This is the way it would look like, what it would look like if you would see it in the field. This is my preferred solution. It's the induced draft version. So again, the fan is on the top, and you have these bundles over here with its water recirculation system and drift eliminators. What makes this very interesting is that one could build it just like an induced draft cooling tower. So one can either collect the water in devices and put into a basin, or one could have a basin at ground level. All right, so what makes this interesting? So the hybrid deflecmator has 15 to 25% of the plot area of an equivalent air-cooled condenser. So it's really a booster. It needs much less. You need much less heat exchanger for the same performance. Its capital cost is 25 to 50% of the capital cost of an air-cooled condenser. It can be incorporated into the IWC induced draft air-cooled condenser. It has no visible plume, which is a major advantage. And standalone hybrid deflecmators can be retrofitted. These standalone units can also completely replace a conventional wet cooling system, which includes a surface condenser pumping system and wet cooling tower. And we found, doing some studies recently, that the system seems to be significantly cheaper than a conventional wet system. So, ATC performance enhancement. How can we improve power plant performance using an air-cooled condenser? So for new builds, definitely look at the induced draft option. Include the hybrid deflecmator modules. Conduct plant-specific studies to improve the performance in general. Apply the latest design rules which we've developed via R&D. Ensure maximum fin tube quality by frequent testing at Stellenbosch University. Ensure maximum fan efficiency by fan testing and by designing fans optimally. Include online cleaning systems, which is a significant component to include. Install wind mitigating devices. Install variable speed drives, and install digital twin online monitoring systems. These all will allow you to be able to generate more power out of a system than before. Then retrofitting, definitely similar sort of approaches. So maximize fan efficiency, increase installed motor power if necessary, install wind mitigating devices. Often these are not included. Install tube cleaning systems, sometimes they're not included. Increase the number of air-cooled fan modules if space allows it, but definitely include or incorporate hybrid deflecmator modules. Install online monitoring and install fogging. This is least favorable. So dry wet case studies that we've done were very interesting. So one study was that one could achieve, by combining dry and wet cooling, one could achieve the same performance as a completely wet cooled power plant, but with 50% reduction in water. And this is incredibly valuable, especially in water scarce areas. So that was one of the first outcomes, which is something to take note of. Then the performance of one hybrid deflecmator fan module is equivalent to 4 to 6 ACC fan modules. What I showed you in the induced draft IWC unit is that just by putting in those bundles, we have 50% more output out of the same plot area, which I think is unique. Then for a plant like Matimba, 10% to 25% or 400 megawatt to 1,000 megawatt increase in power output can be achieved. by adding 4 hybrid deflector modules per 665 megawatt unit. On average, one could achieve 2.5 or 100 megawatts additional output on a plant like Matimba. And this is what is really interesting. The capex of such a retrofit would be in the order of $240 per kilowatt, based on the annual average, with only 14% water consumption of the wet cooling tower solution. So if one puts this into perspective, $240 per kilowatt per kilowatt, a new renewable energy power plant, a concentrated solar, costs you in the order of $8,000 per kilowatt. And a fossil-fired or a coal-fired power plant in the order of $2,000 to $3,000 per kilowatt hour. So this is an absolute no-brainer if one sees the sort of numbers. Then payback periods based on life cycle costs, 2 to 5 years, which is also in power plant terms very, very short. So another improvement is currently ongoing. Chris Meyer is involved. His company increasing the fan efficiency by 10%. Gives you around 7 megawatts, 1.7% increase in power output at a cost of about $600 per kilowatt, which is very good. This also improves the fan performance under crosswind conditions, which gives an additional output. And another spin-off is the 50% lighter blade. For wind, a plant in Belgium, I did a study and we could get up to 3% increase in power output, or let's say 3% reduction in load losses, and much less vibrations. So what the bottom line is, maybe conclusions, significant additional clean energy can be generated economically by combining dry and wet cooling technologies. This is not done often. I know of one plant that's operational in the US, Comanche, that combines dry and wet cooling. And I'm not, there are a number of reasons probably why dry and wet cooling is not combined, but this should definitely be done on every plant. Then combining recoverable, renewable, and conventional energy power generation, I believe is probably the best way to go in future. Maximizing HCC performance can give you dramatic increases in output on an existing plant, and one can optimize operating efficiency by online monitoring, and effectively by adding or improving the systems, one can eliminate recoverable load losses and unplanned outages. At the moment, Minister Ramagopa is really busy on this topic. However, he's just trying to gain back or recover energy that should be available. So there's a current action plan on recoverable energy. But what I'm suggesting is actually new plants or new capacity can be created on existing plants by improving the cold end. Thank you very much for this opportunity. Before I go to my panel, are there any questions at this stage?
Hanno, there are a couple of questions in the Q&A. You can just open that up and then have a look through there. Maybe some of your other panel members would also be able to answer some of those.
All right, sorry, I'm just quickly reading through all of them just to. Okay, let's start with one here. A lawyer question: how do the different cooling systems affect power output? Steam through the turbine power output. Is it a function of the cooling system technology, condensing the steam, resulting in a difference in condensed steam available for heating? would have thought that condensed steam, irrespective of cooling, would never produce sufficient water required for the boiler. Now, how this works, Matthew, thanks for the question, is the steam turbine power output is determined by the pressure difference across the steam turbine. And this pressure difference, the cooling system determines what the outlet pressure is of the steam turbine, and ultimately how much power you can extract from the steam. And if you use a wet cooling system, you can actually create or achieve a much lower pressure at the steam turbine outlet than you can achieve with a dry cooled system. And as a result of that, you get more power output in a wet cooled system than a dry cooled system. So to give you a number, at high temperatures, typically 1 degree different in outlets. Well, the steam in the steam exhaust is a saturated steam, so the pressure is directly coupled to temperature. And what we say is a 1 degree change in the steam temperature in the exhaust gives you up to 1% change in power output or efficiency. At design conditions, typically this is about 2 degrees. So that's what drives the output. So what happens is you have a generator with a capacity, but at high temperatures, you cannot generate the power by the steam turbine that the generator can actually deliver. So by improving the cooling, we can actually enhance the output of the steam turbine and get more out of the generator. And this is available technology, or it's available infrastructure. It's not utilized completely. Then Christopher van der Merwe, is the suction draft tower not also affected by strong crosswinds at the bottom fed force draft unit? Stu, I have the same problem as you. I would expect a lot of wind effect, but speaking to the guys at Key, they actually assured me and said that they experienced no real effects due to wind, which is surprising to me. So to answer, this is information that I have, apparently not, but I would expect the wind to have a significant effect.
Hanno, sorry, just to interrupt you here. I forgot to mention that some of the panelists have to drop off at 3 o'clock. So I'm not sure if you'd like to continue the discussion with them, and then we'll come back to the Q&A.
Yes, okay, that's fine. Yes, no problem.
Perfect. Thanks, everyone. Keep asking your questions, and we'll come back to those at the end of the discussion.
Okay, perfect. All right, so I've prepared some questions. So my colleagues have told me that I'm now putting some philosophical questions on the table. I just want to get hold of them. Just hold on. All right. So what the message that I wanted to bring across is we have a air-cooled condenser, and we have technology that we've developed over years. So the team on the panel, and must say it's a pleasure always working with these guys. They've all been involved in some form of research on recoverable energy systems. So Mike Owen was involved with me on the hybrid deflector. He was a student at the time when we developed and patented the concept. So he was involved there, and Chris was involved on fan developments. And Johan van der Spey was driving the Horizon 2020 project through the university, which did a lot of work on the hybrid deflector. So what we're trying to achieve is, if a power plant is built, it's effectively optimized based on the whole cost model of the power plant. So a fossil-fired power plant generally be optimized, and what will come out is that it requires a dry-cooled system. But this plant has the capability of with the same boiler, of the same steam turbine, actually producing much more power. So the first question that I've put here is recoverable energy is actually the way we want to install a system that actually allows us to harness a lot more out of the power plant. So that recoverable energy, I claim, and I make the statement, recoverable energy power generation is the cleanest and most economical form of power generation. So I would like to ask the panel if they support this statement. I don't know who would like to start. Mike?
Mute button. There you go. Can you hear me?
Yes, I can hear you.
Okay, great. Yeah, Hanno, I think I support the statement. I think it's a clean solution in that you are enhancing efficiency, so you're getting more energy out for the same inputs, and your dirty side of power is normally on the input side. So it's a clean solution to producing more power from the same fuel or energy input source. Your cost is obviously water consumption, and that's something that you have to weigh into the equation, but much less water consumption than if you went for a fully wet cooled plant. Whether it's the most economical solution or not is difficult to say, but the studies that I've done and been involved in, post my student days with PhD students have indicated that there are definitely conditions under which these kind of systems are very, very favorable from an economic point of view. And that depends on the availability of water prices, electricity prices and tariffs, when you get your money and how much you get at what time of day and so on. CapEx, which is, for us here has always been an uncertainty. You have a tighter handle on that now, developing the technologies, but there are definitely conditions in which it is a very economical, or at least, it offers good returns. And so clean, 100% yes, most economical can be, for sure.
Yes, Mike, I think just maybe from my side, why I say most economical, I think I'm comparing it to a renewable central or a concentrated solar plant, which say for Redstone might need 500, 600 hectares of ground. It has an incredibly high capital expenditure, but then again, it has no very low OPEX. And the thing what I'm always wondering is that the tariffs that are paid for that, there's a premium on it, which you probably did not take into account in your study. So some of the follow-up questions will bring up that point. Johan and Chris, do you have anything to add maybe to what Mike said?
Yes. I think that's where the philosophical part comes in. I think one must just be very clear on this. It's you still the way you generate the power is still the same. So it is the efficiency of the plant that improves. So you're getting without increasing as Chris put it earlier this morning, without increasing the pollution or whatever, you can actually benefit more from the plant. So the principle, what you generate, the way you generate stays the same, but it is the efficiency that is improved. So you win more, you get more power without increasing the emissions. And I think that's the important part.
Yes. Thank you. Anything from your side, Chris?
Yeah, I think to a large extent, this represents low-hanging fruit, which is what engineers really enjoy finding in systems. So instead of developing something from scratch, you can beneficiate what is there, which is always a clever thing to do in terms of engineering. And I think that I think the only thing that is unpalatable, there might be other things as well, but what is unpalatable is that it's connected to perhaps a coal-fired power station, and the investor appetite for improvement in coal-fired power stations might not be from a philosophical point of view, or perhaps even an emotional point of view, might not be so strong. But the reality is that some of these pieces of equipment are going to be with us for the foreseeable future. We might as well beneficiate the maximum from these systems. A colleague of mine mentioned that this morning that coal-fired power station is going to be, or has been approved to be built in Germany again. So yeah, I think it is a good idea. You are generating more power, but you are not increasing your emissions footprint. That is a good thing.
Yes, thanks for that. I think that's a good comment. Well, let's go to a next question then. I think why you know, what I said earlier, and maybe repeat it, is that if you design a fossil-fired plant, it's generally based on a parity basis. So that means based on the whole cost of the plant, it's given a certain dollar value that you can invest in every gained megawatt, right? And that's a number that's typically, from all my experience as a power plant design engineer and in industry, is around $1,000 per kilowatt. And that's used to size and select components. And that leaves a lot on the table. Then you go and you see renewable plants, their capital parity is in the order of 6-8 times that, right? So they have a completely different financial model. I want to ask you guys, should one not look at a model which is slightly different for these fossil-fired power plants? That one looks at a part of this fossil-fired plant to be optimized as per normal, and then that recoverable energy component financed in an incentivized way, to be able to sell that as on a PPA basis, or some on a tariff that is equivalent or comparable to renewable energy tariffs. What is your opinion on something like that? Is my question clear? Firstly, maybe you can clarify if something's unclear.
Yeah, Hanno, I think on renewables, you see the sort of financial competitiveness is evaluated on levelized cost of energy, which is agglomerated over the life cycle cost of the plant. And they look at the total outputs divided by capex and opex, right? And that's a much better way to do it, because it's a more holistic cost metric than a capital parity model. So I think using this capital parity model in fossil fuel plants or whatever is short-sighted, and it's not a fair way or a smart way to be choosing your technologies. And I think the hybrid cooling systems can compete on a capital parity basis, because in a new build scenario, you reduce the size of your cooling system for the same cooling load. And so, you know, it's possible, I think, to come in cheaper in that sense without thinking about the power output advantages. But if you start looking at overall energy produced over the life cycle, the fact that energy becomes dispatchable, if you have this recoverable energy, in other words, you can capitalize on peak tariffs and so on, and boost your output when you want it. Then you start to get a model that looks a little bit different in how you evaluate the technologies. And I think if you did that, then you would start seeing these sort of recoverable energy technologies being strong contenders for the best solution for these plants on a financial basis.
Yeah, thanks. That's very good. Anything from you, Chris and Johan? I'm saying you both because you're sitting next to each other. The one of you. Yeah. Thanks, Mike.
I think what I can just echo what Mike is saying. I think once again you need to look at it a bit wider. I think there's in terms of technologies, there's been a great barrier put up against fossil fuel plants, and in terms of financing, institutions have become very reluctant to finance fossil fuel projects, and it is. I would actually always say cost is the cost argument is correct, but there is such a big barrier against financing fossil fuel and that's where the real problem lies. I do think often the problem is that the people financing the projects might not necessarily understand the technology and the implications of the technology.
Yeah, but I think it's a big problem actually for our world, because I think there's so much to gain from this, and one should actually find a way of changing this mindset and informing people. But I think maybe that's a discussion for another session. But the next question does touch on this. You know, we all, I think, except for Mike, probably, Mike, you're not really driving commercialization of technology, but I think Chris and myself, we've been trying to introduce improved technologies into this market, and one of these is now the hybrid deflector. And to be honest, we still need to build one. So this is our drive now to actually get the first plant going. But what are the main challenges? How do we get these recoverable energy systems into the market that they're almost that there's no barrier to implement them? Do you have any views on that? Mike, or let's ask Chris. I think him being also involved in technology development and commercialization.
Well, I think it's very difficult. My impression of the ACC world, and you know, I'm not speaking as somebody who's you know, I manufacture fans and sell them, and you know, I've got two hats. Got an academic hat, researcher hat, and then I've got then I'm also manufacturing fans and trying to get them into a market that has made use of a number of, you know, where fans have been used for quite a number of years. So from my perspective, is that the industry is quite, I don't like to use the word conservative because that invokes some other ideas, but the industry is quite careful to introduce anything that is new. You know, in our case, we went through quite an aggressive bidding process, and we are finally in a position where we are supplying fans to for large-scale use in ACCs. Do I have a magic bullet for convincing people to use new technology? And Hanno, as you say yourself, you haven't built one of these things. And I think if you look at the size of many of these projects, that one understands the reluctance to take on board something that costs a lot of money and that is a new technology. So I think it's, as with most things, it takes time and a lot of effort. Yes. I see there's another question about whether one should do this through legislation, which then again brings in a philosophical component, because I think what we often see is that legislation just makes people more prone to find ways around legislation. So I don't necessarily think that would be an efficient way of accomplishing something. But then again, you know, I'm an engineer. I see we've got a question from a lawyer. Maybe we can ask. Maybe we can ask people more on the social sciences. You know, what the chances of success are on that side. But unfortunately, I don't see a magic bullet. I don't see, at the end of the day, you have to build something, have it tested, and then hopefully people hope that people will notice and recognize that there's an advantage. And that is, I think, usually how things work. In large industries, they are per definition risk averse, I think.
Yes. And I think my comment there as well is, I think just to get the first one built is a risk someone needs to take, and one needs to have a gap just to be able to demonstrate the true capabilities of what one is doing. And that is often the difficult part. And Mike, that was one of your comments in your that you wrote me, which I agree with. Sorry, I just quickly, I didn't realize that my battery was going to go so quickly. Is it on? All right. Yeah. So that's really considering how much much energy and money is going into building these very elaborate renewable systems, which I really support. I think so much less is necessary to actually harness so much more energy, and yet there's no one driving this. I was hoping that this conversation would get people thinking and maybe get a policy undergoing to look into this, so that we can generate cleaner power. So yes, Chris, as you said, I mean, the last question that I had, should one force people to harness energy? For instance, I mean, Eskom, some of the plants are running at really part load, and at sometimes 50% of what they should be producing. So that's a real low-hanging fruit, and that's the situation. That's where we're at. I mean, and we want to actually do better than capacity. We want to improve the performance above that. So there's a lot of work to be done, but I believe that there's an incredible opportunity to drive this recoverable energy. Yeah, those are questions that I had for you. Any question from your side? Yes, Mike.
I know. I just wanted to say on that, so in South Africa, we accept that the dry cooling causes a penalty, right, in terms of efficiency. And in South Africa, that's necessitated by our environment. In other parts of the world, the use of dry cooling is driven by regulation. So they have lots of water in the area. They don't have access to it as power producers because it's allocated elsewhere. So if regulation is driving them to produce lower efficiency energy at lower efficiencies because of water, then surely, they should be thinking about how do we get back towards the efficiencies we had, but without water, or at least without all the water. And I think that's a conversation that needs to be started, particularly in those areas, to say, okay, we accept that we can't do it the most efficient way for us, which is to use evaporative cooling, but how can we get close to that? So that's something to think. But the other thing is in all these renewable plants, there are thermally driven renewable plants, and there as well, I think one should be having the conversation with them to say, well, those plants are often, low efficiency plants because of the operating temperatures and so on, and they stand to benefit from this kind of technology as well.
Yeah, absolutely. What I found was through this visit in the Northern Cape was a power plant like Key couldn't benefit from any of this recoverable energy because there's no real storage. There's very limited storage. So and they have, in summertime when the cooling is poor, they have sufficient heliostats area. So they what was also interesting is that the power output is clipped. So there's a PPA and they have to stick to it. And so often the capacity of the plant is greater than what they're allowed to produce. But what I did find is that on the concentrated solar plants, especially one like Redstone or Ilanga, or where there's thermal storage, that is where one could really benefit from improved cooling. So it would allow, if this is necessary or if it's a requirement, to during the day run the plant more efficiently to store more energy, and during the night to convert that stored energy to power more effectively. So definitely, I think it's an industry where one should really look at this, because what I've seen at all these concentrated solar plants, or many of them, have ACCs, but no augmentation or no evaporative cooling whatsoever. And in some cases, the river is right close by. So yes, food for thought. But thanks for that input, Mike. It's very, very valuable. All right. Should we then anything else from you? Would you like to? Then I think let's go to the Q&A. So shall I share the screen with the questions? All right, can you see my screen? Good, thank you. So, Jerusha, I'm assuming that the technology is scalable. Is it financially
Sorry,
feasible?
I can't see the questions on the screen, but I can see your IW. No, sorry, I can see your IWC background.
All right, sorry.
Sorry, gents, can I jump in here? So the Q&A will just open up on your personal screen. We won't be able to share it on the general screen. But if you want me to assist, just let me know.
All right, thank you. No, I think that's fine. Then I'll just have to read the questions.
Yep.
Go from top to bottom, and I'll see what is prioritized accordingly. So the first one, let's go, Jerusha. You said, I'm assuming that the technology is scalable. Is it financially feasible at commercial scale versus the industrial scale example showed? Maybe you could elaborate on that question. On the commercial scale, look, this is very specific to power plants in our application. So it's very specific to steam plants. So on a commercial scale, yes, one could, but there is already technology available. So what it would take is expertise to actually combine dry and wet cooling optimally on a smaller scale to enhance performance of say air conditioning or refrigeration or these sort of applications. I hope I've interpreted your question correctly. Then the next question is, steam the only medium used for recovery of the heat for further use, or can the technology be custom made for other on-site uses? Jerusha, perhaps, but that one would have to look at it case by case, because I think there's a lot of work ongoing on efficiency improvement, and there are different ways of doing it. So maybe if you would like to contact me with a specific example, then I could give you a more specific answer on that. But look, there's what another message that I think I wanted to bring across is that hybridization is really a way to go forward, because to go back to the power generation. So what we do is in power generation, we say, okay, we don't want to use water, but then we discharge more greenhouse gases into the atmosphere. Whereas on the other side, we save on greenhouse gases, but we use water. And the idea is that one really minimizes all the negative impacts and maximizes the output. And I think that is possible with various technologies. So, I don't know, Mike, would you like to add something there?
Not specifically, Hanno. I think, yeah.
Okay.
Covered. Thanks.
Okay, then Chris, too, I think I answered your question there, or no? Is the suction draft not also affected by strong crosswinds as the bottom-fed force draft unit? So, Chris, no, we've got a lot of experience with cooling towers as well. So, what happens in the force draft arrangement? The fan itself sees very distorted airflow patterns at the inlet of the fan under crosswind conditions, and in the induced draft, this is eliminated or reduced dramatically. So the fan sees much more favorable flow conditions and allows for much better performance, and therefore. This is a significant advantage, one believes, on the induced draft. However, on large scale, I think there still is in being investigated with large CFD analyses. But the initial results show an improvement. And I think one of the things one wants to understand here is that on the force draft worldwide, and I've been involved in this for a number of years, dealing with problems. Where wind has caused failures on the blades of the fans. And this is particularly found in force draft arrangements. So These induced drafts will give less issues on failures on blades as well as vibrations on the systems. I hope that answered that question for you. Matthew, referencing my question above, or is it a function of less parasitic loss required for water cooling, meaning more net energy output? It's twofold. Yes, the parasitic loads are high, but it's more a thermodynamic reason, as I explained before. So it's more that one tries to get the vacuum to be as high as possible, the steam pressure to be as low as possible at the steam turbine exhaust. But yes, the parasitic load is also a factor to take into account. So in the dry cooling, that is much higher than wet cooling. Especially usually on wet cooling, one uses a natural draft tower for a large power plant, which has no fan parasitic load consumption. Johan Kotze, how are you going to clean the hybrid deflecmator bundles in the design? Or are you using RO water? Johan, we've been collaborating closely with a company that does water treatment, and has been doing a lot of work on evaporative cooling in Africa. So we have a good grip on what's required from a material point of view as well as from a treatment point of view. So no, we do not need RO water. However, we have a process where just before switching off the system, we rinse it with RO water, and that RO water is a clean water system that's separate from the makeup and the recirculation system, and this is kept clean, so it's got its own RO plant, and so before shutting off, we give it a good rinse. The other thing is we're running these hybrid deflecmator bundles with a very high water loading to ensure that we have a thorough wetting of the surface. So that is another way in which we keep the bundles clean. But I think one of the issues that people wonder about is the bake out, or when one cuts it down and the tubes are hot, what remains on the tube surface. Mechanical cleaning is possible as well because it's bare tubes. So there's your other way of cleaning. What we found is often that on cooling towers, one gets different types of fouling, so we have a good grip on what, and you yourself know what drives fouling. These bundles are a lot more open and a lot more accessible for cleaning than fill materials, for instance. So look, the water needs to be looked at. So the makeup water, the analysis is looked at, and blending might be necessary between the water that we get and some RO water. I hope that answers your question there. Derusa Joseph, yes, the IWC wet dry cooling system is too similar to a wet cooling tower. Wouldn't this be reducing the overall efficiency, having an air-cooled condenser in line with a wet cooling tower retrofitted to recovery energy? What about the water consumption of the IWC wet retrofit module, especially if this is a principle of evaporative cooling? Yes, Jerusha, obviously we'll have water consumption, but as I've said, it's a lot less than just normal wet cooling. And it's really, when we design the system, it's designed to actually operate at a high efficiency at reasonably high temperatures already. So it'll operate dry most of the time. But when the temperatures get high, that's when one wants to harness or improve the efficiency, because the dry bulb temperature drives your cooling. And that's where one switches on the evaporative cooling system. So water consumption, yes, it is there, but it's significantly less than with a wet-cooled system. But maybe to answer your system, it's very similar to a wet-cooled system, except for that the wet-cooled system consists of, in a power plant, consists of a surface condenser, which is connected to the exhaust of the steam turbine. And then it has a water recirculation system, and it has a wet cooling tower. This hybrid deflecmator has everything in one. And what that helps is that it's a very similar system to an air-cooled condenser. So the people involved in air-cooled condensers can understand it easily, can design it easily, and it's got a lot more less components. So it's I think in that regard much more advantageous than having wet only or conventional wet. There's an advantage which should be explored and exploited. Christo van der Merwe, to be sure I understand correctly, the combined evaporative cooling to cool the air before using it for dry cooling. Thus, a portion of the cooling load is cooled by evaporative cooling, and in so doing enhances the dry-fin through cooled air and high-density air before pre-evaporation cooling. Correct? Clever? I hope so. Thanks, Christo. But to say it's maybe slightly different from what I understand you saying. So it's two systems in parallel. So the dry cooled system, the fin tube bundles, they get cold air that passes through like an air cooled condenser, and that remains the same. But the evaporative cooling system is connected in parallel on the steam side. So when you switch it on, it actually takes part of the steam that should have been condensed in the air cooled condenser. It condenses in that unit, so reducing the amount of steam that goes to the to the air cooled condenser. And by doing that, you can actually condense that steam at a much lower pressure. So you're reducing the load on the air cooled condenser by transferring it to the evaporative cooling system. But the air passing through the evaporative cooling is separate from the air passing through the air cooled condenser. So in the evaporative cooling system, evaporation takes place. So there's moisture that's absorbed by the air, and as you know, that latent heat is the air takes up a lot more energy than just dry cooled cooling. I hope I've answered that question, Christo. Thanks for that, Luca Fantoni from Next. In your induced draft configuration, primary bundles are counterflow condenser. Are these parallel flow condensers or secondary bundles? If yes, is there a risk of subcooling in secondary bundles? Luca, yes, but we have a design. I'm not showing everything on that slide. So in our case, the primary condensers are actually secondary condensers in the typical ACC configuration. So they counterflow condensers, they're phlegmatus style. And then the secondary condenser is actually a co-current downflow condenser. And what you're asking is if at the outlet of that condenser, you won't get subcooling and freezing. But we have a system designed there which will prevent that. So if you'd like to talk about it, I can share that with you. But thanks for that question. You're quite right. Looking at it the way I've presented it, there is a risk of subcooling in the secondary bundles. Unless of course, we build the air-cooled condenser to be absolutely airtight, and we get rid of all the non-condensables, then subcooling should not be a problem. What percentage of OPEX is the power consumption of induced and forced draft fans? Suresh, I'd have to check that. That depends on how you design it. So each one is designed differently based on the evaluation parameters. So I think what you're asking is in forced draft, one has for the same mass flow going through the unit, one has a lower volume flow rate. So one expects a lower fan power to the induced draft case. Quite right, but it's a completely different system when one designs it. So induced draft has much less losses, flow losses. So one can design the fans quite differently to the forced draft. So it's not directly comparable. So to answer your question, one can design them to have the same fan power. I hope so. So Louis, De Beer, can we find alternative financiers that are not reliant on net zero lobby? We need the energy. Thank you, Louis. I agree fully with you. And I was hoping that maybe some financiers are present here today and are listening. But I hope that from this, some people will read what we've discussed today, and maybe we'll find some alternative financiers that see the bigger picture. Thanks for that question. Christopher Namerve, the purpose of your new system is to improve existing air-cooled condensers, not to replace wet cooling tower condensers. So for us in semi-arid areas where wet cooling towers are not environmentally feasible, yes. If I understand your question correctly, let's read it again. The purpose of your new system is to improve existing air-cooled condensers, not to replace wet cooling tower condensers. Yes, but they could replace cooling tower condensers as well. So this is a completely scalable solution. And it depends on how many, what the ratio is of wet to dry cooling, how much evaporative cooling one will have, and ultimately one could replace wet cooling condensers. So it is for semi-arid areas where wet cooling towers are not environmentally feasible, correct. So what we're actually just trying to do is to maximize the output of the plant by using a bit of water, and that water will be a fraction can be a fraction of what would be required with wet cooling. Louis de Beer, surely we have a reduced carbon footprint using IWC system. Absolutely, that's the objective. So what we discussed in the panel was that you know, we're actually creating power output out of nothing, so to speak, because it's already there. So the system is already burning, and what we're doing is we're taking that energy, just converting it better and creating more power output. So if you look at that component that we're adding, there's zero carbon footprint in my view. And that is actually, your question is good in that regard, because that's actually what I want people to understand, is what we're adding is actually has a zero carbon footprint if you're looking at it in an isolated way. And Thomas Harms, an ex-colleague of mine, thanks Thomas. Thomas mentioned here, excellent presentation, thank you team. Some kind of no-brainer. If one opts for an ACC, then one will estimate the loss of plant revenue due to the inclement ACC operating conditions and compare this to the return on capex resulting from mitigating this loss through hybrid ACCs. Of course, within the context of the associated water consumption. No ACC plant designer can omit this calculation. Thank you, Thomas, for that comment. I agree fully, and I hope that the people are listening to this webcast. That concludes all the questions that I have on the Q&A. Are there any other questions? Mike, do you have anything? I see that Chris still around. I don't see him there. I know that Johan had to leave.
Unfortunately, they both had to drop off, Hanno.
Both had to drop off. All right, that's fine. Mike, any closing statements from your side?
Yeah, I think one thing that it kind of links to Christy's question about using this thing in dry areas or arid areas is that what the hybrid unit or system gives you is a large amount of flexibility, or say a larger amount of flexibility in your design, and you can optimize how you combine the wet and dry systems depending on the desired output. So you can attach value to water saving, or you can attach value to dispatchable energy, or you can attach value to maximizing efficiency over time on average, and size and use the water in different ways depending on what's important for you in your specific market context and environmental context. And I think that's what makes this a really powerful idea or technology, especially considering how complicated markets are becoming and how complicated the energy picture is becoming, and what you can and can't do. So I think I'd like to close with that.
Thanks, Mike. That's good of you. Good that you said that. Yes, and I agree. And I think, you know, what isn't so known in South Africa maybe is and much more in other countries, is that there are different tariffs during different times of the day. And peak tariffs are often significantly higher than normal tariffs. And if one has this dispatchability option where one can just switch on some water and cash in on it, that's an incentive for financiers to actually get this technology into the market and get it installed everywhere. So the other thing that I might have just wanted to say, or that I would have liked to say, is that what I saw is in Europe, the tariffs have escalated tremendously. I think a factor of 5 in recent times in some cases, and where plants have been designed with air-cooled condensers a few years back with completely different tariffs. It makes sense to now relook into the revenues and the improvements that could be achieved by putting in a system like this, because the tariffs would pay this back some significant in a very short period, and obviously environmentally it makes absolute sense. Yeah. All right. Shannon, I think that's what I have to say today. And thanks a lot, Mike, for your contributions. I really appreciate that you joined me today.
Yes, thank you very much for that. That does bring us to the end of the webinar. I'd like to take this opportunity to say thank you to you, Hanno Reuter, for facilitating today's proceedings, and of course to our panelists, Professor Mike Owen, Professor Johan van der Spey, and Professor Chris Meyer, who are all from Stellenbosch University. Thank you very much to Industrial Water Cooling for making this webinar possible. Thank you to the attendees for making the time to join us to hear about the cutting-edge concept of induced draft air-cooled condensers for harnessing recoverable energy for power generation. If you'd like more information, please be sure to visit Industrial Water Cooling's website at www.iwc.co.za. The recording of today's webinar will be sent to you in due course, and if you have any additional questions, you can reach either me, Shannon, at creamermedia.co.za, or Christine at iwc.co.za for more information.